Welcome to a video on section 8.6, which is looking at angle measurements and segment lengths in circles. So to begin with, we need to do a definition. We need to define what a secant is. A secant is a line that intersects a circle twice. So it's different than a tangent that only intersects the circle once. So it'll go through it. So you could see right here, this is an example of a secant. It just goes straight through. It could be part of a diameter, or it'll have a chord. Like the chord will be part of the secant that's inside the circle, but the secant itself is the whole thing. So it's related to a chord, just keeps going, or it goes outside of the circle. Okay. All right, so to begin with, we're going to be looking at some different theorems and ideas about angle measurements and segment lengths. And so you can see it's broken up into 4 categories. And in each picture, we're going to find, we're going to have a formula to determine how to find some angle measurements and how to find some segment lengths. Okay, so let's begin. So here we have 2 secants that intersect a circle, or 2 chords if you're just looking at the part inside the circle. So we have this angle right here, angle 1. Angle 1 is not a central angle. It could be, but it's not necessarily going to be. You cannot assume that this is the center. From the picture, I think you could tell that that is not the center. So the theorem basically says, or the formula basically says, the measure of that angle, number 1, is equal to 1/2 times the sum of the 2 arcs, which are x degrees and y degrees. Okay, so we've got this arc right here, and we've got the other arc on the other side. And if we add those up and divide by 2, you will get the measure of the arc in the middle. Okay? Some extra things to keep in mind here is that you could be doing these two. If you found the average, I guess, of those two, you would find, we'll say, angle 2. And angle 1 and angle 2 are supplementary. They make a linear pair. So sometimes they ask, you might have to use that fact to find some arc or angle in the picture. Okay, so let's continue on with angles. The next 3 have sort of the same, pretty much the same formula, but the pictures look different. So let's kind of go through each formula or each picture and see what the formula is. So this is 2 secant segments. So we've got 2 secants. All right, we've got 1 and then 2. Okay, so those are the secants. When we say secant segments, we're just saying it stops right there and doesn't keep going on like a ray or a line. That's all. All right, so we have this angle that is on the outside of the circle created by these 2 segments. Okay, we're going to call that the measure, or that's angle 1. And so basically your formula is you take half, and then you take the big arc x and subtract the little arc y. So this formula I like to think of as half the big arc minus the little arc. Gives you the angle. Okay, so we've got the big arc, which is from x right here. So that's the big arc. And then we've got the little arc, this y, this part right here. So it's very similar to the last formula, except we're not going to add, we're going to subtract. Okay, In the next picture here, we've got one secant segment, which is the one that goes through the circle, and one tangent segment, which just kind of drives by and hits the circle once. You still get the exact same formula. Okay, so again, that was the measure of the angle. Angle 1 is 1/2 times the difference of the big arc minus the little arc. Okay, so again, it's 1/2 big arc minus little arc. This time the big arc is going to be here. It's the x. Oops. Didn't mean to move that. So there's the big arc, there's x, and we got the little arc, which is y. Now the little arc and the big arc actually touch at this point right here. That's kind of one difference. Okay, so that's y. And that gives you, the formula gives you the angle, angle 1 in both cases. I should highlight that. Okay, and the picture is exactly, or the formula is the same, but the picture is a little different. In this case, the third case, we've got two tangent segments. So we have two segments that only intersect the circle once. And you have this angle out here created. So once again, the formula is the measure of angle 1 is 1/2 the big arc, which is x, minus the little arc. Okay, we've got our big arc and our little arc. But one really important difference here is that the big arc and the little arc will make up the entire circle. So in this case, x plus y will be 360 degrees. So this is an important idea to keep in mind, because you often have to use that in this case. But the formula is the same. Okay, so we're going to talk about segments, but first I'm going to go over some of the examples with just the angles. So number 1, again, this is not the center. Even though it looks very much like the center, you cannot assume it's the center. Okay, they have to give you some indication that that is the center. So instead, we're going to be using this formula where we take sort of the average of the arcs. So we're going to take 88 and 86 and add them up and then divide by 2. So the angle on the inside is equal to 1/2 the sum of those two arcs. So you should be able to tell that that's not the center, because if it was the center, those arcs would be the same. It'd be vertical angles here, and they'd both be the same, but they're not. It's actually going to be, you calculate this out, 87 degrees. It's right in the middle. Between that, it's an average. Okay, let's take a look at number 2. Okay, so this is a case where we have the angle on the outside. It's created by two secants. So we have a big arc, which is 90 degrees, and we have a little arc, which is 20 degrees. And so this is the formula where we're going to do the big arc minus the little arc cut in half. So the angle x, which is what we're looking for, is going to be equal to 1/2 the big arc, which is 90, minus the little arc, which is 20. So we subtract, and we cut it in half. Okay. The next two, 3 and 4, are using that same formula, but using it in a different way. So here we have a tangent and a secant. So we're going to do big arc, which is unknown to us right now. We're going to have to find this, minus the little arc, which is what we're actually looking for. That's the x, equals the angle, which is 38. Okay. So how are we going to do this? Okay. We need this arc to find the answer. And there's no way to find that exact measurement, but we can write an expression for it. This big arc is the, well, we got the whole circle would be 360. If we subtract off the 140 and subtract off the x, you would get what's left. So we're going to think of this as 360 degrees minus 140 degrees minus x. If we clean that up a little bit, combine these two together, that would be 220 degrees minus x. So that's what I'm going to use for that. So this one's a little bit more challenging than the last one, definitely. Okay, but stick to the formula. Okay, it's the angle, which is 38 degrees, is equal to half the big arc, which is, we now have an expression for that, 220 minus x, minus the little arc, which is x. Okay, so again, the angle on the outside equals 1/2 the big arc, which is this 220 minus x that we found, minus the little arc, which is x. So now this becomes an equation we need to solve. So let's combine our like terms here. So 38 equals 1/2 times 220 minus 2x. Okay, that's nice. They're both even now. So when I distribute this 1/2, I'm cutting everything in half on the inside here. So 38 is equal to 110 minus x, because I basically divided each by 2. Okay, and subtract 110 and then take the opposite of that, or you could just do 110 minus 38 and that'll give you the answer. If you do it this way, you're going to get negative 72 is equal to negative x, or 72 is equal to x. So 72 degrees was our answer. So if you needed to find the big arc, you could do 220 minus 72. So this arc is 148. This arc is 72. And if you did 148 minus 72, cut it in half, you would get 38. So it works. Okay. Number 4 is a little different again. We've got 2 tangent segments. So we have the big arc, which stops at the point of tangencies. We've got the little arc, and then we've got the angle. Okay, so once again you run into this situation where you don't have something for the big arc, or maybe sometimes it's you don't have something for the little arc. Remember that this arc, the big arc, and the little arc have to add up to 360 degrees. So if I subtract 360 minus x, that's what's going to be the orange arc, the big arc. Remember, in this case, they make up the whole circle. Okay, so the angle, 60, equals 1/2 the big arc, 360 minus x, minus the little arc, x. Okay, the little arc, the big arc, and the outside angle. All right, let's do the same thing we did before. Let's combine like terms and then distribute and just solve. So let's see. That's 360 minus 2x. I'm going to cut it in half. That gives me 180 minus x is equal to 60. I could do that in my head. X would be 120 degrees. And then this is going to be 240 degrees, 360 minus that 120. Okay, so those are angles. Let's talk about segment lengths. So we're not talking in degrees, no 360s, no 180s. These are not angles, these are segment lengths, so different. Okay, so here we have two chords, which are like parts of secants, and they intersect in a circle somewhere, not necessarily at the center. And so what we get is that A, which is this piece right here, multiplied times B, which is the other part of this chord. So A times B will be equal to C times D. The products are the same. What this comes from, and what, in fact, what all of these sort of ideas come from, is you could connect this and connect this, and you would have similar triangles. You'd have vertical angles, and then they'd be sharing this chord right here. So this angle would be congruent to this angle. And so you have similar triangles, and so what we're writing is it comes from a proportion. Okay, it was A over C is equal to, let's see, D over B, and then you cross multiply. That's what this theorem is coming from. All right, the next two cases are very similar to each other. And these also come from similar triangles, but it's a little bit harder to draw it in here. It gets a little complicated. But you could draw two similar triangles, and then it becomes proportional sides and things multiply. Well, I'll show you like one of the triangles. If you draw this, that's supposed to be straight, it was terrible, and this, you've got this triangle right here, and then you've got this other triangle over there. You can prove that those are similar, and then their sides are proportional. Okay, but I'm just going to keep it simple. Okay, this idea, or this, to find this relationship, is going to be the outside. So the outside piece of the secant segment here. So that would be W right there. That's the outside, or one of the outsides. So the outside times the whole thing equals the outside times the whole thing. So I remember this as the outside times the whole equals the outside times the whole. So W is the outside times the whole, not X, but this whole thing, which would be X plus W. If you were doing the whole thing, you'd have to add them up. And then it would be equal to the outside times the whole. So the outside will say Y times this whole thing, which we would say is Z plus Y. So putting it all together, W times X plus W equals Y times Z plus Y. Outside times the whole equals the outside times the whole. Oops, forgot that. Okay. The next one down is pretty much the same idea, except you have a tangent. And in this tangent, the outside and the whole thing are the same thing. So it kind of becomes the outside, this piece, times the whole, which is, it's also the same thing, equals the outside, which is Y, times the whole, which is Z plus Y. But because you're multiplying t times itself, it becomes t squared. So I think of this as the tangent piece squared equals the outside times the whole. All right, so we've got this piece, which is the t squared, the tangent, equals the outside, which is the y, times the whole, which is z plus y. Now, I included it for completion's sake because it fits into this so well, but we already did the one where we have two tangents. That's just the case where they're congruent. So AB equals BC. We don't need to really practice that one again, but I just want you to remember that that's there. All right, let's do some segment examples. Okay. So remember, no angles this time, no degrees. So this is a tangent and a secant, so we're going to do the tangent squared equals the outside times the whole. Okay, so our tangent is y. So that's what we're going to square. We're going to do y squared. Our outside is 2. And our whole is 11. Make sure you're adding to get the whole, not multiplying. Use the segment addition postulate. Okay, so there's our whole. Okay, now we just have to solve. So y squared is equal to 22, square root both sides. We do not need a plus or minus because we're dealing with length here, so the negative would not make any sense. And then the square root of 22 is about like 4 point something, 4.7. Round or simplify as required. Okay, number 6. Here we've got two chords. This is the one where you do the product. So x times 10 equals 6 times 5. So 10x is equal to 30. So x is 3. So the products have to be equal. They are not equal. Right? If this is 3, which it is, then one of these is 11, the other one's 13. They're not congruent. Okay. One more for the basic ones. Outside times the whole equals the outside times the whole. Now, this one's a little bit harder because we have the outside, which is z. The whole is going to be z plus 12. So we have the outside, which is z, times z plus 12 equals the outside of the other piece, which is 4, times the whole, which is 12. 4 plus 8 is 12. This is going to end up being a quadratic because we're going to have to distribute that, and that's going to be z squared. So that makes this one a little bit more challenging. And then 4 times 12 is 48. Okay, so when you have that quadratic, set it equal to 0, see if you can factor it. If you can't, you'll have to use the quadratic formula. So I'm going to subtract 48 from both sides. I'm going to see if I can factor it. It would be a diamond problem. So I don't think that this is factorable. It feels like it should be, but it's not. There's nothing that really works here. So if it's not factorable, you can solve it in a different way, such as the quadratic formula. Okay, so x equals negative b. So negative b plus or minus the square root of b squared is 144 minus 4 times 1 times negative 48 all over 2 times 1. Okay, now you'll get two answers, but you only want the one that would make sense, which would be positive. All right, and it looks like when I worked it out, I got about 3, that's not a negative, about 3.17. Okay. I would like you to try on your own the last 3 problems, and there will be a place for you to check it. All right, good luck.